Yes. What we want to do now in our small lectures or in our lectures on hydraulic modeling is we want to introduce instead of a block rain model, we want to introduce groundwater reservoirs. So we want to have one river stretch as it is shown here, but with groundwater cells around this stretch of rivers. So again the river's geometry, we have again the river's geometry with some compartments. The compartments have an upper boundary and a downstream boundary. So everything what is going into the compartment will be calculated, what is going out from one compartment will be calculated, but we have a third volume flux which is coming from the groundwater going into the river. I just called it QR here, going into the river from the groundwater to the river, which is QR. So the water depth in one compartment in the river is calculated according, first of all, calculated from the incoming flux, from the outgoing flux, and from the flux coming from the groundwater, which I called QR here. So, and now the catchment area or the total system looks like this. We have something in blue like some river compartments. This is now a view from above, on the system. So we have, this is one river compartment, this is the next river compartment. It's, of course, these are very wide compartments, this is the next river compartment, and so on and so on. And here in green, these are the groundwater compartments or the soil elements. So we have one river compartment, and lying adjacent to this river compartment, there's an catchment or entrainment compartment, which is this one. So this has the same length as the river compartment, but it has a different width. It can, normally the groundwater elements have a much larger width than the river. A river has something like a width of 10 to 100 meters, and the groundwater or the soil compartments can have a width of, I don't know what, 1 kilometer, 10 kilometer, or whatever. So the width of these two things is totally different. So, and now we want to describe first of all the mass balance in these soil elements and the discharge going to the river or the river discharge going into the groundwater elements. But first of all we have to describe the soil itself, because the soil is not a river. So the most important thing what we have to look at in a soil is its porosity. The porosity is defined as phi is the volume of fluid divided by the total volume. So this is the porosity of a soil, the volume of fluid or the volume of porosity divided, or the ratio of pores divided by the total volume. So fluid plus solid. So this is fluid, this F, and this S is solid. So when we look at a soil, then this, for example, is the whole volume, and here we have some soil S volumes defined by the particles, and the pores here are the gray-shaped areas where water can be in the soil. Normally, the soil or the porosity of a soil is dependent on the grain size diameter of a soil, and classically we can estimate at least the porosity of a soil from the grain size of a soil, showing in this small slide here, but I don't want to go into details on that. Otherwise we should have measurements on the porosities coming from geotechnics, that we can introduce the porosity phi in our simulation element. Okay, and what we want to do now is to balance out the mass, or to describe the mass balance, the mass of fluid of water. The mass of fluid is the density of fluid, rho, times the volume of fluid, the change of volume of fluid. So in the volume of fluid is the total volume times porosity. total volume times porosity is the volume of fluid. So when we take the total volume, which is the height of the groundwater free surface, ZGVS is the height of the groundwater free surface. This is the area of one element. This is the porosity, and this is the density of water. So the total mass change of water is actually the change of the groundwater free surface, the porosity, the density of water, and the cross-section. In that way we can calculate the change of water. This is actually when we only look to precipitation. Then it's the rainfall. Niederschlag in Germany is rainfall or precipitation. So this is the mass per time going to the soil as precipitation. The mass per time is density times volume per time. And volume per time is density times cross-section of our bottom times intensity of rain. IN is intensity of rain, meaning such an amount or such an height in a certain time. So, and when we look at this part of the equation, and at that part of the equation we can cancel out A, which is the cross-section of our element. We can cancel out the density of water, and we come up with porosity times change of groundwater level is equal to the intensity of rainfall. Actually, this is not correct. This is a huge simplification, because we assume that the rainfall is now going directly into the groundwater. Rainfall in this differential equation is going directly to the groundwater, which is actually not the case in nature, because we have unsaturated areas of soils above our groundwater level. But this is the first simple model to describe a groundwater model. Yes, so, and now we want to solve this kind of differential equation, but next thing what we introduce is we have also a coupling of groundwater cells with our river. So here you see in blue or in brown blue, here you see the groundwater level, and here you see the river. And the brown areas here are unsaturated groundwater, and the blue-brown area is saturated groundwater. So, and when the groundwater level is larger than the river level, then water goes, or then there is a runoff into the river. When the river is higher, when the river level is higher than the groundwater level, then we have something because of rainfall or because of flooding or something like this. Then we have a river flow into the groundwater. And river flow into the groundwater. And now we want to calculate the flux of groundwater. And in the easiest way, we can say that this flux of groundwater going into the river, or river water going into the groundwater, is proportional to the difference of the free surfaces. When the free surfaces are at the same height, groundwater free surface and river free surface are at the same height, then there is no flux from the river to the groundwater, or vice versa. When the river free surface is larger than the groundwater free surface, then there is a river flux into the groundwater. And when the groundwater level is larger than the river height, then there is groundwater flowing into the river. So this difference is very important. It decides about the sign of this flow, or the sign of this flow, and of the amount of this flow. And of course, if the wetted perimeter or circumference, if the wetted circumference of our river is large, then there is a large cross-section between river and groundwater. So we need the circumference of the river, which is here, this, and the length of our river system, which is L. So the discharge, the runoff, for example, Q, is calculated as the circumference of the river times the difference between the groundwater level and the river free surface. And what is missing is a time. What is missing is a time that both sides of the equation have the same unit. which means cubic meter per second. So here's a time, and this we introduce as a parameter, as a leakage parameter, and we have to describe our system with this leakage parameter, and we have to tune this parameter to get good results. So when we take into account rainfall and runoff, then we have a differential equation for the groundwater. The groundwater is changed due to precipitation intensity and due to freshwater discharge to the river or river water going into the groundwater, which is this term. So this is a full differential equation to describe the groundwater free surface. And this we have to solve in our numerical model. So I would like to show you some lines of our code, So first of all, we now have to define in the definition part of our code, we have to find the river width and the groundwater elements width, which I say it's 10 kilometers for every element here in this. Then, of course, we have to define for every groundwater element the porosity, of course, and the leakage rate. The leakage rate telling us how, yes, this is something like a time that the groundwater goes into the river or the river water goes into the groundwater. This is the leakage time. This is empirical parameter in this kind of numerical model. So for every element, I take for every element the same width and the same porosity and the same leakage time, but you can change it from element to element or whatever you want to do. Yes, then we need to simulate now two kind of equations. First of all, the river equations, and second of all, the groundwater equations. We have two sets of differential equations. We have not n element equation. We have 2 times n element equation. One n element equation for this, for the river, and one n element equation for the groundwater. So, first of all, we introduce initial water depths for the groundwater. The initial water depth of the groundwater should be the same water depth as in the river, just in simplification. And now we call the differential equation solver again, or in this simulation here for 1,000 hours. And now the solution is river solutions and groundwater solutions. I just write it in an array of river levels of n element river levels and n element groundwater levels. So, and then again I plot it. For the function, for the mass balance function, it does not change very much. I just introduce here the circumference of the river, which is the width. Again, we assume a rectangular cross-section. So the circumference of the river is the width times 2 times h for the lateral boundaries. Then I introduce rainfall events, calling a function rainfall. Then I calculate the flux going from the groundwater into the river or from the river into the groundwater, which, as I said, is the groundwater level, the river level, minus the groundwater level divided by the leakage time. And here you see how I solve river equations and groundwater equations. Here, this equation is going from 1 to n element, so this h is a river h. And here, this h goes from n element plus I. So it's the next n elements here. So these are the groundwater elements. I just divide up the array between n element river elements and n element starting from n element plus 1 going to n element 2 times n element. These are the groundwater elements. So, and then I define the river mass balance, which is the same mass balance as we had last time, just with a groundwater flow here, or a runoff flow, and the groundwater differential equation, which I had already shown you in this lecture. This is the groundwater. So this is going from I equal to 1 to n element, and this is going from n element plus I, so it's the next part of our solution array. Yes, rainfall will be defined the same as in our last lecture on the block rain model. So we have this is a rain in element 2, this is a rain in element 5, this is a rain in element 20. Actually, we don't have 20 elements. So the height of rainfall is 5 centimeters, here it's 5 millimeters, here is 10 centimeters, and so on. So, and the rain starts Ti in this element, in element 2, it starts after 100 hours, and it has a duration of 10 hours. 10 hours, and in this 10 hours, there are 5 centimeters of rainfall. So a very slow, or a very, yes, not a strong rainfall here. So this rainfall starts after 150 seconds. It durates about 2 hours, and it's only 5 millimeters. So you can change these numbers as you want, and we will see what's happened. Yes, and this is a function where we define the rainfall, or we introduce the rainfall in our numerical model, and I think that's all. So now we can start the code. Now we can start the code, and the code is something here. Let us see what happens. Again, we have our river filling up with water. This is the water height. This is the bottom of the river. The black line here, the blue line is the free surface. And when you see, now it goes a little bit up, as you see. Now it goes here a little bit up. These are the rainfall events. And at the end of the simulation, there's a longer rainfall. And always, when there's a rainfall, it goes up at some points. And also the free surface goes up. Where is the rainfall? Let me see. It runs and runs. You have to wait a little bit. No rain. No, it goes up a little bit. No, yes, it went up a little bit, and after a certain while it goes down. So this is not very interesting. You have to define a little bit more rain. I stop the simulation. You have to define a little bit more rain, but you can see in the time behavior of the system where you see the rainfall. So this is the water depth in the river. Unfortunately, this is German, but this is the water height at certain elements in the river, and this is the groundwater water height. So we see some small rain events here. So this is the first rain event filling up the groundwater, and then the groundwater goes slowly down because all the water goes into the river. Then there is a next rain event here in the element 3, and then we see a rain element here and here. And the same you can see here in the river, but it's a little bit later than in the groundwater, because first of all it fills up the groundwater and then it fills up the river. So these are the time series of our simulation, and you can now play with the numbers a little bit and see how the rain changes the discharge in our river.